All right, welcome back, future engineers. Today, we're diving straight into an explainer on how to transform black box AI into actionable, crystal clear water policy. Look, if you've ever built a highly accurate predictive model only to have stakeholders completely reject it just because they couldn't understand how it worked, well, you are in the exact right place. We're going to bridge that massive gap between complex engineering mathematics and real-world environmental regulation.
So picture the stakes here. You've got your state-of-the-art AI, and it predicts a really poor water quality index, or WQI, for a critical drinking water reservoir. Naturally, the Minister of Environment looks at you and asks, why? What exactly is driving this pollution? If your only answer is, I don't know why, it's just what the algorithm outputted, then the minister is simply going to say, then I can't use it. Perfect model accuracy is literally entirely useless if it can't drive real policy decisions.
And that is exactly why we're focusing on explainable AI today, or XAI. Think of XAI as AI that actually shows its homework. It's the ultimate engineering tool to make those complex machine learning decisions transparent, interpretable, and, this is absolutely crucial, defensible in court or regulatory hearing. We are turning your black box into a glass box.
Here is our game plan for this explainer. We'll hit the black box problem, then the engineering ML toolkit, the methodology pipeline, decoding XAI charts, and we'll wrap it all up with a student quiz battle.
Okay, part 1. The black box problem in AI water policy. Let's define the challenge and look at our real-world data set. We're looking at a massive case study here. The Danjiangkou Reservoir in China. It supplies critical drinking water and targets really strict Class 2 standards. Now, our goal is calculating the water quality index. That's a single number, summarizing the overall water health based on different weighted parameters. We're working with a robust data set, right? Nearly 2,000 water samples, 1987 to be exact, collected over 6 years across 31 sites, tracking 8 key parameters, like pH, dissolved oxygen, and biological oxygen demand. But again, computing the WQI from all this data is only half the battle. If we use a black box model, all that data means nothing to a regulator.
Moving right along to part 2, the engineering ML toolkit. We need to write algorithms to crack this explainability problem. Look at this lineup of models. One specific algorithm just totally dominates. Extreme Gradient Boosting, or XGBoost, is our absolute heavyweight champion for WQI prediction. It boasts an incredible R-squared of 0.975. That means it explains 97.5% of the variance in the WQI with a remarkably low root mean square error of just 1.96. But you know what its true superpower is for us engineers? Native SHAP support. It was literally built to integrate perfectly with the explainability tools we're about to use. Random forest and neural networks are great, sure, but XGBoost is exactly what you want for this job. All right, part 3, the methodology pipeline. Let's trace the exact roadmap from raw data to publication.
We've actually boiled down a really comprehensive 9-step methodology into these 6 core phases. Think of this as your blueprint. You kick things off with rigorous data pre-processing, handling those missing values and outliers. Then you calculate your target WQI using established standards. After that, you split the data, train your models, and evaluate them with your metrics. But phase 5? That's the magic step, the XAI application. That's where you apply SHAP for your global insights and LIME for local insights before finally reporting your results and linking everything back to the UN Sustainable Development Goal 6 for that Q1 journal publication.
Next up, part 4, decoding XAI charts. This right here is the core masterclass, so pay close attention. Before we dive into the data, let's set some quick visual ground rules. For the correlation matrix we're about to see, dark red means a strong positive correlation. So as one goes up, the other goes up. Green is a negative correlation, and yellow means they basically don't interact at all. Keep that in mind. Okay, check out this matrix. If you scan across the rows and columns, zero in on that dark red box, intersecting total nitrogen and ammonia nitrogen. See that 0.97? That is a near-perfect positive correlation. For an engineer, this is exactly the kind of critical insight you have to flag for policymakers immediately, because treating one of those pollutants is basically guaranteed to impact the other. Now, this is where it gets incredibly practical. This line plot is what I like to call your local single story. When the minister asks you about one specific monitoring site on one particular day, this is the exact chart you bring them. Here, our model predicted a highly polluted WQI score of 85.6. And look at those massive green bars for BOD and ammonia. Lime is showing regulators plain as day exactly how those high levels explicitly drove this one specific sample up into the polluted zone. It's targeted, it's local, and it leaves no room for confusion.
But what if stakeholders want the global big picture? What if they ask about the entire river system? That is where the SHAP waterfall plot comes in. On the right, you can physically trace the math, step by step from the baseline expectation at the bottom, which was around 55.6, all the way up to the final prediction at the top. It fully decomposes the model's decision. Meanwhile, that bar chart on the left ranks the parameters by their average impact across every single sample in the entire reservoir hintile.
So to read SHAP like an absolute pro, you just need to remember these rules. Positive red values push the prediction higher. And since a higher WQI means dirtier water, red is bad for water quality. Negative blue values push the prediction lower, meaning better water. And because of the additive property, all these values sum up perfectly to your final score. The massive, unavoidable takeaway from the Donjianko study: ammonia was the undisputed #1 driver of pollution across all 31 sites. Which brings us to part 5, the student quiz battle. Get those activity sheets out. Let's simulate a rapid-fire quiz to see how well you've actually mastered this material.
All right, first challenge. Think back a few minutes to our visual tools. Which specific explainability method do you grab when the minister asks you to explain the pollution in just one specific river sample taken last Tuesday? Lock in your answers.
If you said lime, you nailed it. Local, interpretable, model-agnostic explanations. Remember, SHAP gives you the grand global overview, but lime perturbs the data locally to explain a single, isolated prediction. It's your single-story tool.
Okay, question 2. Think back to our engineering ML toolkit. Out of all the models we evaluated, which one absolutely dominated the performance metrics with an R-squared of 0.975?
That would be XGBoost, Extreme Gradient Boosting. It is the current undisputed champion for wiki prediction, and we love it because it integrates natively with SHAP. Top-tier accuracy meets top-tier explainability.
All right, the final and definitely the hardest question of the explainer. Say you run your SHAP analysis, and you get a positive SHAP value of 12 for the turbidity parameter. How do you translate that specific mathematical value into plain English for a policymaker?
It all comes down to the scale. Because a higher WQI score means dirtier water, a positive SHIP value tells us that parameter is pushing the score up. So a plus 12 means turbidity is actively driving the WQI up by 12 points, which is actively worsening the overall water quality.
So, you've mastered the methodology, you know how to decode the charts, and you crushed the quiz battle. But all of this leads to one final critical question for you to take home today. How will you leverage explainable AI in your own master's proposals? Are you going to keep building block boxes that sit on a shelf because policymakers don't trust them? Or are you going to bring radical transparency to the world's most critical water sources? The toolkit is yours. Go make the complex crystal clear.